I'm Antonio Sala. In this video we are going to discuss how to compute the time response of an electrical circuit with two resistors and one capacitor when subject to a sinusoidal pulse 1/2 period. In this video we are going to use the concept of causality to compute the solution in a piecewise way. In a companion video we have discussed exactly the same problem but using some delay and superposition notions, of course yielding the exact same solution. This is the electrical circuit and the governing equations. So giving parameters some numerical values and computing the Laplace transform of the equations, we got this model in the Laplace domain, transfer function times input plus initial condition term, being the initial condition the initial capacitor voltage. The time domain pulse has this expression. This is its plot, 10 milliseconds, half period. And even if we, of course, could use its Laplace transform to obtain the time response, we will not do it as such in this video, because we will understand it as an input coincident with the red sinusoid, this one with this Laplace transform. The input is coincident with it in the first 10 milliseconds. The yellow delayed version was used in another video. We will not look at it in here. So the basic idea we are going to use here is causality. If the blue and the red inputs are identical in the first 10 milliseconds, the outputs will also be identical because the output at a given instant cannot depend on features of the signal that occur in the future. So this is the basic idea. Once we get to this instant, we will reset the clock and think about a zero input in some initial conditions. So we will just use U and S, the Laplace transform of the sinusoidal, in our developments. Let's go with the details. We will first compute the response to a sinusoid starting at instant 0 and lasting forever. So this y1 will be the transfer function, this one times the Laplace transform of the sinusoid plus this initial condition term. If we carry out usual partial fraction expansion and inverse Laplace transform, we did it in detail in the companion video in which we used superposition, so we are not doing here. This will yield the exponential term, this thing will yield the cosine term, and this thing will yield the sine term. So this is the output to a sinusoidal input, which I plotted here in the red line. So we have some initial transient and then we reach the steady state sinusoidal regime. Note that we are starting in non-zero initial conditions. So good. What's next? Well, now we realize that from this point onwards, our actual input is not this sinusoidal because it is 0. So this is wrong. And of course, this means that from this instant onwards, the output computation is also wrong. So we cannot use that fragment of the response. But by the causality ideas we mentioned earlier on, we can be sure that as initial conditions and input in my sinusoidal pulse problem are coincident with this solution in the first 10 milliseconds, then the first 10 milliseconds of output will be correct. So that fragment will be valid for our problem, being the rest striked out invalid. So what's next? Well, basically Our next problem will be solving from this initial condition a modified problem with zero input. Let us first see the end, and we'll delve into the details later. My initial condition of the second fragment with zero input, the yellow one, well, this initial condition will be the final condition of this 10 milliseconds of fourth fragment. This is the idea. So let us compute this initial condition and then compute this free response, which will be an exponential. I denoted y1, the solution to the whole sinusoidal, this red stuff here, so its value at 0.01 is what I need. And here is it. It is 0.73. So this final condition of the fourth fragment 1 will be the initial condition of fragment 2. Of course, if we had a circuit with, let's say, a higher order, 2 or 3 capacitors or whatever, then initial conditions would be a vector of charges or some variable and its derivatives, etc. But we'll just keep it simple for the moment being. So with this first order stuff, we have just one initial condition, which is the capacitor charge of 0.73. So which is the time response from these initial conditions? Well, we had this stuff, which is not a transfer function because it does not multiply an input, but it's kind of something used that had to be multiplied by the initial condition. So this is it. And if I take the inverse Laplace transform, it will of course be this exponential. But look that I explicitly indicated that I have a new time variable. Why? Well, because the differential equation solvers and the theory of initial conditions think that in here, which is the initial condition instant, the clock must read 0. So I need a new clock that reads 0 in this instant, so that the inverse Laplace gives me a result according to the theory. So this is the output, and then in order to plot it, I just need to state in here that the new clock is just the old clock minus 0.01. When the old clock ticked 0.01, new clock ticks 0. So this is the way to plot what I computed here. And then here we have the purple exponential decay at the right place in the time axis. So by stitching the red fragment 1 and the purple fragment 2, I get the whole time response. So this ends our calculation. Of course, it is coincident with the dashed black line we obtained in the companion video with the superposition method 1. So this is it. Let us conclude. In this video, we have computed the time response of a first order system subject to the blue pulse plus no pulses at all from 0.01 onwards and non-zero initial conditions. In here we have the non-zero initial conditions. We have obtained the solution in a piecewise way, first computing a fragment of the output to a whole sinusoid lasting forever, and then saying that that solution was valid for the first 10 milliseconds, but invalid from that time onwards. So we computed the initial conditions of the second fragment as the final conditions of the first fragment, and computed the time response with the new formula for the input, which was 0, the yellow horizontal line down there. So with this methodology, we can compute the output to piecewise inputs based on causality and on the concept of state, saying that whatever happened in the past It is summarized in the charge of the capacitor at this instant. Future will only depend on the capacitor state in this instant, and it will not depend on which input waveform or initial conditions were used in the past to reach this voltage. Causality, independence on future inputs, and the concept of state, independence of past inputs given current state, are the main conceptual ideas that enabled us to obtain the solution we have presented here. Thanks for watching, and subscribe if you wish to.